Now we haven't yet learned a trick for differentiating exponential functions. So we're going to go right back to first principles and use that to differentiate y equals 2 to the power of x. Now we could pick any number, 3 to the power of x, 4 to the power of x. We're picking 2 because it's nice and simple and it gives us a number to work with. And then we can look at what would have happened if that 2 had been another number. Now, we already know this formula. We've seen it before. F dash x equals the limit as h approaches 0. You need to write that every time until you actually take the limit of the function of x plus h minus f of x all over h. Now, summing in, if our function is y equals 2 to the power of x, then the function of x plus h just means sub in x plus h anywhere that there was an x in the original function. So we get 2 to the power of x plus h, don't we? Then we need to subtract the original function itself and put it all over h. On the next line, I've taken this 2 to the power of x plus h and recalled that that's the same thing as 2 to the power of x times 2 to the power of h, because I know from my index laws that if I multiply these together and the bases are the same, I'd need to add the indices, and that would give me this. So it's like working backwards here. Now, why have I done this? Well, because I've noticed that it then gives me 2 to the power of x times 2 to the power of h, and I've got another 2 to the power of x over here, so I can actually factorise. So on the next step, I've factorised and said this term and this term both have 2 to the power of x in them, so I'll bring that out the front of some brackets, and that gives me 2 to the power of h minus 1 inside the brackets all over h. Now, you'll notice that this whole section here doesn't have any x's in it, okay? And you'll also notice that this part here doesn't have any h's in it. Now, as we take the limit as h approaches 0, that won't actually have any impact whatsoever on 2 to the power of x, will it? Because it has no h's there. So what we can do is see that this 2 to the power of x is actually not going to be needed to be included in the limit. We can actually multiply, find the limit of this section that does have h's in it, and then multiply it by 2 to the power of x. So what I've done on the next line is I've actually taken this 2 to the power of x and I've brought it out the front so that it's out here, so that it's separate from the limit. Now, why have I done that? Well, let's have a look at what I am actually differentiating in the first place. I'm differentiating y equals 2 to the power of x. And what I've got is I've got 2 to the power of x, so that seems sort of neat to have that out the front. And then I'm multiplying it by another section that doesn't look neat and tidy at all. In fact, it looks quite complicated. This section that looks complicated, though, it doesn't have any x's in it. So what that means is that as we look at different values of x, this isn't actually going to change. It's sort of like a constant, or at least it's a constant for this curve that has 2 as the base. Now, when we look at this and try and use our algebra to tidy it up, there's not much we can do. We can't divide each of these parts by h because we've got different bases here, and that won't help us take the limit as h approaches 0, so we're actually stuck at this point. Now, when mathematicians get stuck and trying to figure something out, we come up with a solution, and the solution here is to say, let's take that whole nasty looking part here that we're not sure what to do with, because it seems algebraically quite hard to deal with, and let's just call that m. Now, what is m? Well, I've defined it down here. I've said let's let m be defined as the gradient of our function at the y-intercept. Now, how did we get to that? Well, let's have a look. Remember that if we find f dash 0, that's really the gradient of f of x when x is 0, isn't it? Or in other words, when x is 0, that will be our y-intercept, won't it? And we know that y equals 2 to the power of x looks something like this. It goes through this point here, when x is 0 and y is 1. Now, why have we chosen to find f dash 1 when we were busy trying to find a general statement for f dash x? Well, we've done that because we got stuck, so we needed to look for a workaround. The reason this is a good workaround is because the only place that we need to sub x in to our derivative here is here. And if we sub in a 0, then what we'll always get is 1. And we'll get that no matter what the base is. It could be 3 to the power of x, 4 to the power of x, anything to the power of x. Anything to the power of 0 is going to be 1. So if we look at that saying, let's see if we can use that, I'll have 2 to the power of 0 times this awkward looking part, which I've chosen for the moment to call m. Now, how have I known to define m as this gradient of the y-intercept? Well, 2 to the power of 0 is 1, so really all I have here is m. If by definition f dash 0 is the gradient when I am at the y-intercept, then this m, in other words, all of this stuff, must be the value of the gradient right there. So what we find then is that for all of these sorts of exponential curves that have, you can put any number here that you like, when you differentiate them, what you get is a multiple of themselves. You get themselves times by this constant. And it will be the same constant for that graph no matter what value of x you look at. But of course, different curves will have a different m value because they'll have a different gradient right at that point. Now we can make this into a more simple looking rule. If I rub out this part and just write down what we've learnt here as a general rule, what we've found is that if you differentiate anything to the power of x, then what you get is you get that same function multiplied by m, where m is, by definition, the gradient at the y-intercept. Now, we'll come back later in the course to find out exactly how to find this m, because there's some tricks to it, and every single value of a, each curve will have its own m. So we can put a box around that as a rule that we've learnt, and we can also add a statement. In other words, when you differentiate an exponential function, you get a multiple of itself. Now, it makes sense to study an exponential function that has a really nice m value, and that's where we get the exponential function e to the power of x, because it has an m value of 1. And what that means is that when we draw it, as it goes through the y-axis, its gradient right here is 1. And in fact, its gradient at any point will be exactly itself.